Okay, here we go. All right. Can't believe that it locks on me. No, I don't need this one. I think. Hey, you know what? I forgot to put the file to myself, but you guys have the new file, right? The example number set 2. You have that? Excuse me? You do have that, right? It begins with example number 11. Do you have that? Hello?
The file that you posted yesterday,
Yes,
right?
yesterday. You have that, right?
Yes.
It begins with example number 11. You know, please keep the first page empty because you will need the space underneath the beam. Okay. What I am going to write right now, you should try to find some space to write in some other places. Okay. Yeah, how could I forget that? Anyway, so, but it would be nice to keep that. It's okay. Okay, let's begin right away. You have a beam that looks like this, right? Let me try to draw the beam first. Oh, okay. Black would be better. You have the beam that looks like that. Okay. All right. That's with the moment of inertia equal to I for both spans. Okay. And this is 8 meters long, and that's 12 meters long. All right, and we have the uniform load here of 3 tons per meter. You know, I don't draw the beam very beautifully because I'm gonna need to draw it again when I start doing the moment distribution. But, you know, let's say this case is pretty easy, but still, when you set up the slope deflection equation, it's like you're gonna have to write some equation before you can come up with sigma mb equal to 0 and so and so. But in moment distribution, we will begin our step number 1. And notice that there is not even a need to identify the degree of freedom. You can just start right away. Because after all, the moment distribution is just a mathematical solution for slope deflection. Okay, so step number 1, I can say that's relative stiffness is what I need. Okay. Please try to write the relative stiffness in the next pages, or try to squeeze in the space, you know, on the side, because you will need the space underneath the beam to do the moment distribution. Okay, so leave the space underneath the beam open, leave it available for you. All right. So let me give it some name. Let's say this is A, B, and C. Okay. So that I would know that my KAB is I over 8. KBC is I over 12. In fact, maybe I should write always on the node program because it writes much better than on the PDF, you know. And now with the say the least common number to be 24, you know, I can say that this is equal to 3K and this is 2K. So now we have the relative stiffness. The next is to see the distribution factor. In this case, when we talk about the lock and release process in moment distribution method, you see joint A is already locked and joint C is also locked. So almost you don't have to do anything because they are originally locked. The only problem that you have is joint B, which can rotate. Okay, so it's joint B that we will focus on. And this time you see that I need the distribution factor at joint B. Correct? And now joint B, is formed by the joining of the member AB and BC. So that means I need the distribution factor of member AB. And before I do that, I shall calculate the sigma K of joint B. Now joint B is formed by member AB and BC. So that means I have 3K from member AB and 2K from member BC. So sigma KB is 5K. All right. So that means the distribution factor of member AB, which is KAB, over sigma KB is simply 3K over 5K. And for member BC, it is KBC over sigma KB. So it is 2K over 5K. Notice that, you know, the denominator here is always the total stiffness. So that means when you add up the distribution factor at one joint, you should always get 1. Correct? So this is 0.6 and this is 0.4. So when you add 0.6 and 0.4, you get 1. And this also tells you that member AB will contribute 60% in balancing the moment at joint B. In the meantime, member BC will contribute 40%. The distribution factor is the ratio of your stiffness. And it can be clearly seen from here that the stronger member will help resist more moment. Okay, in this case, they all have the same moment of inertia, but member AB is shorter, and therefore it is stiffer. And because member AB is stiffer, it will help contribute in balancing moment at B more than member BC, which is less stiff. Okay, so now the third one is the fixed moment. Okay, in this case, it's pretty simple. Fixed moment of member BC, it is minus WL square over 12, which is equal to minus 3. L is 12 square over 12, so that is gone. So it's minus 36 ton meter. And this is equal to minus FEMCB, which in turn becomes 36. So right now I am ready to do moment distribution, okay? So I don't think I can, yeah, but this one is short, so I can do it. So I am going to write my beam again. This time I hope that it's more beautiful. 8 and 12. Okay, so that's a joint. And 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So actually my beam looks like that. Okay, now I'm going to set up my moment distribution. Okay, so here it is. Okay, here we go. Not very straight. Can't leave it that. Okay, straight line. And this is my joint B. Okay. The distribution factor of member AB is 0.6. So I'm going to put 0.6 here, so that I know member AB will help contribute 60% and member BC 40%. Okay, and I'm going to draw the line here, and perhaps I need another line here, and then here. This joint A is already fixed, so we don't need to release it or anything. So the moment that is already there, we're there. So the distribution factor is 0. You don't need to release it. And likewise, here is 0. Okay? And now we have the fixed end moment here. So the sigma fixed end moment at joint B only comes from member BC, which is minus 36. Okay, and that's on the left of member BC, and then you have one more on the right, 36. Okay, so when you released it, you know, because BC is not the true fix, we fix it so that we can calculate this fixed moment. All right, so when you release it, you need to balance it, and you need moment equal to 36. Need 36 so that your sigma MB becomes 0, correct? It's that simple. You need 36 to add up with minus 36 so that it becomes 0. And we have distribution factor. So 60% is going to come from member AB. So 60% of 36 is 21.6. You may take note that this comes from 60% of 36. Okay, member AB helps 60%. That is why this is equal to 0.6 multiplied by 36. Be careful of the sign. Your unbalanced moment is minus 36, so you need 36, and 60% comes from member AB. And 40% comes from member BC. So this is 14.4. Okay, and you again may take note that this number is 0.4 multiplied by 36. So you see, this is 0.6, this is 0.4. So in the end, it should add up and equal to 36 automatically. All right. And that is the end of a so-called the first cycle of your balance. All right. So I can put an end to this. First cycle. Now, what you should notice from your first cycle is that whenever you sum your moment in each cycle, you see, when you sum everything up at joint B, your sigma moment is 0. So you can always check whether or not you have done things correctly after each cycle, because by the end of each cycle, you need to balance your moment, and therefore your sigma moment will always be 0. Okay? Now, we have our new moment here. So that means it will have to be carried over to the opposite end. Okay? So what is our carryover factor? It is a half, right? So that means a half of this and a half of that will be carried over to the far end or the opposite end. And that is 7.2. And this is 10.8. Okay. And this moment goes into the support where it is already fixed. So there is no need to do any balancing act because it is already fixed. You don't need to release the joint. And so the process of this analysis comes to an end. That's it. See how easy that is? Right? So in the end, you sum up all the moment. Okay? Just try to use the different color. Okay? So in the end, you sum everything up in the vertical direction. So right here is 10.8. It becomes your end moment. Right here is 21.6. Right here, you sum these two up together, you know, it all comes down here, and you bet it's minus 21.6. Notice how, you know, equilibrium is maintained, and here you sum this up. So it becomes how much is that? 43.2. Voila, that's it. The end of your moment distribution. And again, because this is sort of the derivative of slope deflection. So the sign convention is the same. You see, that means this is positive, so it is clockwise. This is positive, so it is clockwise. This is negative, so it is counterclockwise. This is positive, so it is clockwise. Okay? Which makes sense, you know, because you have the load only on one span. So this is negative, counterclockwise. That's the direction of your internal moment. Clockwise, so it's that direction. Help resist that. Okay, this has to be clockwise to balance it, and therefore that has to be clockwise. Okay, notice how true it is for the carryover factor. This is twice greater than that. So whenever you have the moment here, whatever the number is, the half of the value will show up on the far end. Okay, pretty easy, right? That's it. Question? Okay, no question again, huh? So I think it's high time that we begin the next adventure. Question?
Can you explain about 10.8 and 7.2 again, please? How can it come?
Okay. All right. So thank you for your question. Let us begin from beginning. Okay. So because you may be busy, you know, writing, so you missed something. So in the beginning, let's say you understand how we can obtain the distribution factor, right? So the distribution factor comes from the ratio of the stiffness. That's why we got 0.6 and 0.4. And ladies and gentlemen, please pay good attention. When you see the member, when you see the moment of inertia, and when you see the length of the member, you should be able to sense which member is stronger than the other. And the stronger member should always have the greater value for the distribution factor. And the distribution factor in one joint should always add up and equal to 1. Now you put your distribution factor in your beam, you have the moment, the fixed end moment. And this fixed end moment becomes the unbalanced moment at the joint. This minus 36, which is unbalanced, must be balanced by member BA and member BC, which form joint B. How much they help in balancing this minus 36 depends on the distribution factor here. And in balancing minus 36, you need 36. And so 60% will come from member BA or AB, which means it's 21.6, which is equal to 0.6 multiplied by 36. And then 40% of the rest will come from member BC, which is equal to 0.4 multiplied by 36. So once you have 21.6 and 14.4, this is the moment on your member. So whenever there is a presence of this member, the opposite end will feel the presence of this member. Ooh. One moment. Okay, back to business. Okay, the far end here will feel the presence of this 21.6 and how much it should feel. We have approved that 50% of this value will be carried over to the opposite end. So it is always, 50% that will be carried over to the other side. So this 21.6 multiplied by 0.5, which is the carryover factor, will be sent to the far end. So 50% always of the moment here will be sent over to the far end of the member. And 50% of this 14.4 again will be sent to the far end of member BC. That's why we have 10.8 and 7.2. 50% of the moment that you have here. That is the job of the carryover factor. Okay. Does this answer your question?
Yeah, thank you, teacher.
Okay, cheers. All right. So we should have a lot of time before the next break. So let me try to finish another problem for you guys. Okay. And if you get confused with the procedure, please interrupt me so that you don't drag your confusion over until the end of the problem, okay? Because believe me, if you are confused due to the procedure, many of your friends will have the same problem, all right? So I think I'm gonna need to add a few more pages. Let me do that right away, okay? Okay, so the next problem, it will not be as easy as this one, okay? So let me again write the beam and try to calculate the small things before we begin. So, again, now you know that you're gonna need the space like this, underneath the beam. So please leave the blank space underneath the picture of the beam that I give you, okay? And try to find some other space to write down the distribution factor and fixed moment and so and so, all right? So this time we're gonna have the 3-span beam, small fun. Looks like this. Okay, with the point load in the middle and then the uniform load. All right, and I give different I. It's just the value is somewhat relative. 20, 20, and 10. The span length is all 10, I believe. That's 5 and 5, so it's a 10 as well. So that is also a 10er. Okay, so from here, we can calculate our relative stiffness. Okay, so your KAB, it's just 20 divided by 10, right? Very convenient, it's 2. And KBC, that's also 20 over 10, so it's 2. And K of member CD, that's 10 over 10. Sorry, that's 10, but you know that, right? It's 1. So right now, I can say that sigma KB is 4. And sigma KC C is now 3, right? So from this, I can calculate my distribution factor for each member. Okay, so let's move on to the next step. Step number 2. I'm just going to use the nomenclature now. So it's distribution factors of member AB, but again, joint A is the fixed. So if we focus on joint B, let me call this distribution factor BA. Okay, that's going to be equal to KAB over sigma KB, which is 2/4, which is 0.5. And then distribution factor BC, at joint B, it's KBC over sigma KB. And again, it's 2/4, right? So it's 0.5. Notice how, that is 1. Okay. Next is distribution factor CD, right? So that's KCD over, it should be CB first. CB, so it's KCB, which is KBC over sigma KC now, so it's 2/3, right? You can say it's 2/3 or 0.67. And distribution factor, that's it, right? No, I'm confused. CD, yeah, it's from joint C. It can be confusing at times. So it's KCD over sigma KC now. That is 1/3, right? Or 0.33. Again, that is 1. All right. Now, the next step is the fixed moment. Now we have 2 spans, okay? So we have span BC and span CD. So my FEM BC is minus PL over, thinking about the square, PL over 8, so it's minus P is 20 tons. You guys got that in the document, right? L is 10. I think my focus is gone berserk. Over 8, so that's minus 25 ton meter, and this is equal to minus FEMCB, which becomes 25. Sorry, becomes 25. Another one is FEMCD, which is minus WL square over 12. So that's minus W is 1.2, L is 10 square over 12. So that is equal to minus 10 ton meter, and this is equal to minus FEMDC. Okay, so we have set ourselves up to do the distribution. Okay, so you guys ready? Should be, right? I hope that I have enough space for you. So probably too much, okay, too long, but okay, I'll try to do that. I don't need to write the beam again, should I? Can I skip that? You have the beam, right? And this is your joint B, this is your joint C, okay? So at joint B, distribution factor from member AB and BC are in fact equal, which is 0.5. So you can have your 0.5 there. And you can have your 0.5 there. Okay, look like 5, so let me try again. Okay, and here BC and CD at joint C, this becomes 0.67. You can say 2/3, it's up to you. And this is 0.33. Okay, so this is joint B. Let me drag down here like this. This is joint C. Okay, you don't have to drag down at these two ends, but let me say that joint A is fixed. So again, it is naturally fixed. So your distribution factor here is 0. All right, maybe a little line here to help our procedure. But joint D now is a simple N, and the moment there must be 0. And it's simple, it means that member CD is all alone at joint D. Nobody is going to help balance the moment. So the distribution factor here is 1. Okay, so now we can put our fixed end moment in and become our unbalanced moment. This is minus 25. This is 25. This is minus 10. And this is 10. You guys ready? I hope so. So it's time to balance this. You need plus 25 to balance this minus 25, right? And 50% is going to come from member AB, and another 50 is going to come from member BC. So without further ado, member AB will give 12.5 for the course, and member BC will give 12.5. Okay? So you notice that sigma moment here is 0. Now let's move to joint C now. We have more numbers, and you can see that this time your sigma fixed end moment at joint C is in fact 15. Okay, the unbalanced moment now is 15. Is the total of fixed end moment at joint C. So to help balance that, you need 2/3 of minus 15. Okay, so let's say you need minus 15 so that your sigma moment becomes 0. All right, and 2/3 of that is going to come from member BC. So 2/3 is minus 10. And 1/3 is going to come from member CD, which is minus 5. Notice that again, sigma moment at joint C will become 0 because you have plus 25 here and then minus 25 from these 3 terms. So sigma moment is 0. And the last place, this is 10 all alone, so you need minus 10. That is the end of your first can use this cycle. Notice how, you know, right here, sigma moment is 0. Right here, sigma moment is also 0. And right here, sigma moment is also 0. Okay? That is the end of one cycle. Your sigma moment is 0. All right? So it's time to carry the moment over to the far end of the member. All right? Because you have 20.5 here. So when you have 20.5, a half of this must exist across the member. So that is 6.25. Okay. This exists here, so a half must exist at the opposite end, 6.25. And minus 10 exists here, so a half of that must exist at the opposite end, minus 5. Likewise, minus 5 here, so minus 2.5 there, minus 10 here, so minus 5 here. So because the presence of the moment would mean that you need to carry it over to the far end of the member, so you have new unbalanced moment coming in. And you need to balance this again. Okay? So this time, this because at joint A is already fixed, so we don't need to do anything about it. Anything that goes into joint A will remain there because it is already naturally locked. But joint B, you have a new one coming in that's minus 5. You don't have to go back to the first cycle. The first cycle is balanced. But you have the new unbalanced moment coming in, so you need to balance minus 5. And again, here you need plus 5 to balance it out, right? So a half of plus 5 will come from member AB. So again, you have 2.5 here. And then another 2.5 from member BC. Notice that sigma MB in the second cycle is 0 again. And right here at joint C, now the total of the unbalanced moment is 1.25. So you are going to need minus 1.25 right there, right? So I don't know if this helps, but let's say you need minus 1.25, okay? And 2/3 of that is going to come from member BC and 1/3 from member CD. So that is minus 0.83, and that is minus 0.42. And this again, there's no help. So 2.5 is just going to come from member CD alone. That is the end of the second cycle. Again, notice that if you look at this second cycle, the sigma moment here is 0. And the sigma moment here should be 0 as well. And likewise, the sigma moment here is 0. Okay, notice how at the end of each cycle, sigma moment must come down to be 0. So if you do every cycle correctly, in the end, when you sum the moment, it should all be, you know, 0. So that means you can always check yourself at the end of every cycle, just to make sure that, you know, the results are correct in the end. Because notice how you don't need to solve any equations at all, but it's just the mathematical procedure to reduce the moment 50%, 50%, and 50% after each cycle, so that in the long run you would know that the number will dwindle down to 0. But there will be a lot of numbers involved, so you need to stay focused, remain calm, don't rush yourself. Okay, if you can check yourself at the end of each cycle, you are likely to maintain your position. If you become harsh, you want to finish the things quickly, you know, and so, you may easily make some kind of human errors along the way. Okay, so with that said, this one, we have this presence of moments. Again, it must be carried over to the opposite end. That is about 1 1/4. This here will come minus 0.42. This will go 1 1/4. This will go minus 0.21. This will come here and 1/4. So you have new unbalanced moment coming in, and we need to balance it again. And please hold on to your horses, because the burning question will be, where will it end? It will end, right? Because you see the number is dwindling down. But do we need to keep doing this until it becomes 0? I will answer that shortly, but let me try to finish this. So again, third cycle, we have this minus 0.42 coming in, so we need plus 0.42, so it's 0.21 here and there, and right here it's 2.5, so you need minus 2.5, 2/3 coming from member BC, so that's minus 1.67, and here is minus 0.83, and right here is business as usual, no help. Okay, and again, that's the end of the third cycle. Notice that you can also check that, you know, this third cycle, you know, the sigma moment is 0. Okay, and here too, and here too, and we just need to go a little bit further. This will be carried over, let's say 0.11. This 1 1/4. I'm sorry, 0.11 as well, right? Here is minus 0.84. Here is 0.42, minus 0.42. and that is 0.11. Okay, and again, the balancing act begins. You need 0.84, so 0.42, and then 0.42. This is 0.22. So this number is down, but this number goes up a little bit because of the fluctuation from, you know, joint C. So this is minus 0.15, and this is minus 0.07, and this is 0.42. That is the end of your cycle. Okay. Again, you can check that this summation of the moment in cycle number 4 must be 0. This is 0, and then this is 0. Okay. Now you can stop when, you know, you see that this moment is less than 3%. Okay. So this is a little bit big, so I can go one more cycle. So right here it's 0.21. Okay. Say 0.08. Oops. Zero 0.8. This is 0.21. This is 0.21. And this is about minus 0.03. Okay, and do it one more time. I get that 0.04 here, 0.04 there. This is 0.42 in total. So this is minus 0.28 minus 0.14. And right here is 0.03. So that should be enough. The number is closing down to 0, and I can end my procedure. And sum up everything now. I can do that. So I will sum everything up, you know. Coming down here. All right, so that is 7.82. It's my final moment. And I can sum this down. That is 15.67. And I can do the same with this. Just all come down here, and you bet it should be equal to minus 15.67. Notice that if you check and at the end of each cycle, your sigma moment is 0, it means that left and right are equal and opposite in each cycle. So if each cycle is done correctly, in the end, you should sum them up and should all be correct. If you sum them up at the end and left and right are not equal and opposite like this, you just need to go back and check every cycle. And let's say if you find out that, oh, your second cycle is wrong, you just need to go over everything again. So it would be wise to check at the end of each cycle that you do your work correctly and precisely. Okay. And the same here, right here, you would expect, yeah, you should get something like this. So it's 19.89 minus 19.89. Okay, and right here, you bet, because, you know, it's a simple n, so it's 0 in the end. Okay, so let me try to finish this before we have a break. But one of the few things you should notice is that first, you can finish when you know the balance moment is less than 3% of the original of the numbers you begin with. So for those who do not carry out enough cycles, you will be deduct points significantly, because I'd say you don't recognize the importance of numbers. Okay, you need to try to bring this number down to within 3% of the original value here. And second, always finish by balancing the carry over moment. Okay, so in other words, you must finish every cycle. There, from time to time, there'll be students who carry the moment over like this and don't balance them. So when you carry the moment over and you don't balance them, it means that one of your cycles is not finished, and therefore in the end your sigma moment will not be zero. And to me that spells disaster, because it could be viewed as you don't know what you're doing. Because as a civil engineering I'm not going to say student, but no, as a civil engineer, you should know that your equilibrium must always be satisfied. So when you carry the new moment over to the joint, you don't balance them. That means you leave your structure, unbalanced, and you don't have your equilibrium. Okay, so you would always finish your cycle. All right. Is there any question? You want me to go over anything?
Can you indicate the number that the comparison 3%? Which number?
Man. There. See, blood.
You begin with.
So you begin with your fixed end moment. Your fixed end moment becomes your unbalanced moment. Okay. And okay, you okay? Crystal clear?
And sorry.
Okay, go ahead. Go ahead.
Example 25 compare with the 0.08, right?
Sort of, yes.
Okay.
But you shouldn't compare with this. You should compare with this 0.04, because 0.08, this is the moment that is carried over. You need to balance it. Okay.
Okay.
And one more thing that I should write before some of you do, and I think this would not help. Don't go crazy about numbers. Every year, every time, there will be someone who write this with like 5 decimals, and because they are not so sure when they should stop, they would do it like 20 cycles, and the number, and because the number is getting less and less and less, you increase your decimals. So in the end, you summarize like 5, 6, 7, 8, 9, 1, 2, 3, 4, whatever. You can do this, but you don't write it, okay? Don't show it to anyone. keep it in your paper somewhere, or don't throw it. Okay, this doesn't show that you're good. It shows that you don't know anything about numbers. Don't be a slave to your calculator. It's true that, you know, if you keep your number, in the end your moment will become 0, because there is a chance of you rounding off the number. And you know, the very popular question is it okay, teacher, because you know my moment on the left is 0.1 different from my moment on the right? I understand why you asked the question, but you should understand the importance of significant figures and how you round the number off, okay? That is the thing that has been taught to you in year 1 in the university, I believe, the significant figures. Because I was taught the significant figures in the first year as well. But it's only natural that it becomes the first thing we forget. All right. So yeah, you don't see the importance of using it until you actually use it. Okay. So thank you for your question. Is there any other questions? So let me stop the share and let me go back to our room, stop the record.